As promised, let's take a look at an example problem that applies stress concentration factors to determine how much force that we are allowed to apply to our member. Go ahead and check out the example. In this example, we have a bar that has a hole in it, as well as a bar that has fillets in it to a reduced cross-sectional area. We're given that the maximum allowable normal stress is 120 megapascals, and all the geometrical properties of the bar. So based on our discussion on stress concentrations, we know that we are likely to have a stress concentration occur at the inside of the circle, so where I marked it with an X, as well as at the fillets at the beginning of the fillet radius on the smaller bar. Because again, the average stress in the smaller portion of the bar will be higher, and then above and beyond that average stress, the actual stress at the corner of that fillet will be even larger, hence a stress concentration. Let's calculate the value for the maximum stress at the hole. We're going to use the formula for the stress concentration factor in conjunction with the average stress to figure out what this maximum stress has to be. In order to determine the stress concentration factor from the plot, we need to calculate the ratio of the diameter to the width of the plate. So the diameter, or 2r, is going to be 20 millimeters. That was defined in the problem statement. And the width of the plate is given as 50 millimeters. So 20 divided by 50 results in 0.40. To use the plot, we enter on the x-axis at 0.40. We come up vertically until we meet the line, the curve. Then we proceed from the curve to the y-axis, and this will give us our value for k. In this case, k is 2.18. It's important to recognize that we are obtaining this value for the stress concentration from a graph. So whenever we use a graphical method, there might be some wiggle room in terms of what the actual number is, depending upon how well you interpolate from the graph. But 2.18 should get us pretty close to the correct answer. Keep in mind that the curve that was used to generate this stress concentration factor, so that blue curve, also probably has some variation from the test results. Now we can calculate the maximum stress. The maximum stress is equal to k times the average stress. In this case, the average stress, if we look at the little insert on the graph, is equal to P divided by W minus 2R times T. So remember, this was the average stress for that reduced area around the hole. So plugging in our numbers, K is 2.18. We don't know yet what the force is. That's what we're asked to calculate, the maximum load that can be applied. The width of our plate is 50 millimeters or 0.05 meters. We subtract out the 2 times the radius or the diameter of 20 millimeters or 0.02 meters. And we multiply by the thickness, 10 millimeters or 0.01 meters. We set all of this equal to our maximum allowable stress. Our maximum allowable stress is 120 megapascals, or 120 times 10 to the 6th newtons per meter squared. So I've gotten everything into newtons and meters, so all my units should cancel out. And I can calculate my force. My force will come out in newtons, and the answer actually comes out to be 16,514 newtons, or 16.514 kilonewtons. So we would expect at this value of load a failure to occur at the inside of that circle. Now we want to check the portion of the bar where we have those fillets that are leading to the reduced cross-section. So let's calculate the maximum stress at these fillets. So again, I'm going to follow the same process, except it's a different curve to use to find my stress concentration factor. So I calculate the value for the radius divided by h. H is the width of the smaller portion of the bar. So the radius is my radius of my fillets, which is given to us as 12.5 millimeters. And then h is given to us as 25 millimeters. And you can check the geometry at the top of this page. So that gives us an R to H ratio of 0.50. We also have to check W to H ratio, which is going to be 50, the width of the wider part of the plate, over H, 25 millimeters, the width of the smaller part of the plate. Then we'll take this information and go into our graph. This graph has a lot of different blue curves, so I'm going to zoom in a little bit so we can see a little bit better. Based on our W over H ratio, which was 2.0, I want to select or identify the curve that corresponds to W over H of 2.0. If you have something that falls between one of these curves, you are able to interpolate from this graph. So I want to use this curve, so you have to follow that line over to the curve. And in conjunction with my R over H ratio of 0.50, I'm going to come up from my x-axis from that value of R over H until I meet the curve that matches W over H of 2.0. Then I go over to my y-axis and I see what value of K I calculate. I pull K of 1.40 off of this plot. So then the solution follows the solution above. I set up my maximum stress, sigma max, equals K times sigma average, and I'm able to then solve for the maximum allowable load P that I can apply to this bar. In this case, sigma average is P divided by H times T. So this is the cross-sectional area for the smaller portion of the bar. So my maximum allowable stress is 120 times 10 to the 6 pascals. My stress concentration factor was 1.40 as determined from the graph. And then I set up my maximum allowable force, P max, divided by H, which was 25 millimeters or 0.025 meters, times the thickness, 0.01 meters. I can now solve for the maximum allowable load, P, and that is 21.429 kilonewtons. So now I see that based upon failure at the hole, I can get up to 16.514 kilonewtons, and failure at the fillets is 21.429 kilonewtons. The problem asks me for the total maximum load that I'm allowed to safely apply to the connection. So I need to figure out how much load can I safely apply. Well, as soon as I get to 16.514 kilonewtons, I will initiate failure at the hole. So we say that failure at the hole would control, and therefore the maximum allowable load that I'm able to use in this particular problem using the stress concentrations is 16.514 kilonewtons, because once I go above that, I would initiate failure at the hole even though I don't have failure yet in the fillet region. I hope you enjoyed learning about stress concentration factors as well as temperature effects and applying the force method in today's lesson. I hope to see you back soon. We'll be talking about torsion next.